So let's talk about how to solve second-order ordinary differential equations in Matlab. This is really more in line with the main discussion of the course. And that's, as an example, you've got some ODE which looks like this. I'm just making something up now. 6y dot plus 5y is equal to 7, something like this. So this is someone you probably already know how to solve by hand. But it's a second order ODE, okay? So it seems like we're going to need to use different things, different techniques to solve this compared to what I just talked about with the systems of ODEs. But in fact, you don't need anything new. So the kind of thing that might be a little bit surprising is that a second order ODE can be written as a system of two first-order ODEs. And let me show you how that works. So for this example here, I would have y double dot is going to be, let me put everything else on the right-hand side. So I'll have 7 minus 6y dot minus 5y. And then I'm going to think of y dot as a new variable. Let me call it v for velocity. So then I would have y double dot is equal to v dot, right? Because y dot is v, so y double dot is v dot. So then my ODE looks like this. V dot is equal to 7 minus 6v minus 5y, right? So now it looks like there's two variables, v and y. So I need two ODEs. There's one, and the other one is just the definition of v, right? Y dot is equal to v. So this is a system of two ODEs. For v of t and y of t. Of course, v and y are related by the second equation here, but I've converted my second order ODE, single second order ODE, into a system of two first order ODEs for v and y. Okay? So since all of that work we did earlier, we learned how to solve systems of ODEs, I can convert a second order ODE into a system of ODEs, and I can use those techniques. So we'll use the examples to do that. Or I'll use some examples to show you how to use those techniques from before for second order ODEs. So just in general, I did a specific example on the previous slide, but a second order ODE you can write like this. Y double dot is some function of t, y, and y dot, right? And now I think of y dot as a new variable. A new variable. So then I have two first order ODEs. The first one is v dot, or let me write the first one like this. The first one's going to be y dot is equal to v. And the second one is v dot is equal to f of t, y, and v. So I have this system now. And then I can use all the techniques from before. So here's an example. Let's do the simplest example of free fall. So free fall, ball falling with no air resistance, has gravitational force downward, mg, and so we get the ODE sum of the forces F equals ma. So I get sum of the forces is equal to ma. And so I get minus mg is equal to mx double dot. And so I get x double dot is minus g. I can write this as two equations. I get a system of equations. The first one is, so maybe I better call it y. Let's call it y, just to match with above. So the first one is y dot equals to v. And the second one is v dot, which is the acceleration, is minus g. So I've got, that's my free fall, ball falling with constant acceleration, written as a system of two first order equations. So now let's solve this equation using the two methods that we learned earlier in the lecture, using Euler's method and then ODE 4.5. Okay, so here I'm going to solve the second order ODE for the free fall of the ball. And I made some initial conditions. So the initial height is 10 meters, initial speed is 5 meters a second until the ball hits the ground. So let's use Euler's method here. Okay, so remember, what does my system of equations look like? It looks like y dot is equal to v of t, right? And v dot is equal to minus g. Okay. So what I did here, let's go through the code. The first part is just defining all of the variables. What I did is I defined a function here, and this function is v dot, right? So a function, it depends on t, y, and v, and it's equal to minus g. In this case, it's a constant, but you could change that if you had a more complicated function. The next line is just initializing the arrays for t, y, and v. So the first entry of t is t0, the second entry of, the first entry of y is y0, the first entry of v is v0. And I'm initializing some loop variable because I'm going to use some while loop here. While loop, while y is bigger than 0, so as long as the ball has not hit the ground yet. Now I do my Euler's method. So how do I find the next value of v? I take the previous value of v plus the slope of v, which is the acceleration. In this case, it's just equal to minus g, but I'm calling that function that I defined up here, in case I had a more complicated function, times delta t. How do I find the next y point? Well, the next y point is the previous one plus the slope of y, which is what by definition that's v times t. And then of course my next time step is just my previous time plus my time step. Right? Increment the loop variable, go back and do this over and over again as long as the ball is above the ground. Okay, so you're seeing Euler's method in action. Remember, I've got a system of two first order ODEs, one for y and one for v. And so each time through the loop, I need to increment each one of those. Each one gets updated every time through the loop. And that's it. So I'll show you when I run it. Of course, you know the exact solution in this case. Like you can go back to your high school equations for kinematics and you know exactly what the equation looks like. So you can plot this numerical solution along with the exact solution for comparison. Of course, the purpose of this code is that you can use it for things that you don't know the exact solution for, but I'm just showing you for comparison. So let's see what it looks like. Okay, so here it is. The black line is the exact solution, which you can solve by hand, and the blue dots are the Euler's method solving a second order ODE with Euler's method. And it's pretty good, not great, because it's Euler's method, it's not perfect, but it gives you a basic idea of how to solve an ODE numerically. Okay, and then now on the next slide, let's go ahead and see how this looks if we add the ODE 4.5, use Matlab to solve it using all of its full power of its built-in functions. Now let's try to solve the same problem using ODE 4.5. So the trickiest part is defining that vector f, which is the vector for the ODE. So let me remind you what we're going to do. We're going to write the system of ODEs, which looks like this. Y dot is equal to v, v dot is equal to minus g. We're trying to write it as a single vector equation. So I'm going to define u vector is going to be y and v. So the first entry of u is y, and the second entry of u is v. And then my system of ODEs, which is here, can be written as a single vector equation, which looks like this. U dot is equal to the following vector. So y dot is v, so up here is v, and then v dot, which is the second vector, is minus g. And so I'm defining now this thing is going to be my vector f, and it's equal to, first entry is v and the second entry is minus g. Now the tricky part, remember, is that I need to write v in terms of u. So v here is the second entry of u. So what I will write in here is u, second entry of u, u of 2. And then minus g is a constant, so I can just put it there. So this is how I'm going to define my function f in Matlab. So remember, I find this to be the trickiest part, is you take your ODE, and then everywhere you find so everywhere I see y, I would replace it with u of 1, which is the first entry of u here. And then everywhere you see v, you replace it with u of 2, which is the second entry of u. Okay, so that's the plan. Now I'll show you on the next slide what the code looks like. Here's the script. So again, the first 5 lines is just defining the variables. And then this line here is the tricky one. So that's defining that function f. So I defined it just the way that I wrote on the previous slide, just here, right? So my vector f is the right-hand side of that system of ODEs. And everywhere I have a y, I place it with u of 1. And everywhere I have a v, I replace it with u of 2. So there it is. There's the f function. I've got u0, so that's my initial point. So my initial point is y0 as the first element, v0 as the second element. Here's my list of times that I want to know the solution at. So I'm solving it from 0 up to 2.0 seconds in steps of 0.1. And then here is where I call the ODE 4.5 function, store the results in those two matrices, T solution, U solution. Now remember that U solution here is a matrix. The first column is going to be the Y solution. So again, U is this vector here. So U is a matrix. The first column of U is going to be Y. So I'm going to have a list of y points, and then the second column of u is going to be v. So I'm storing those two solutions, y and v. I'm pulling out the particular columns of my u solution. All right, so the code is quite simple. I've posted a similar code on D2L, which you can use to play around with. And then on the next slide, I'll just show you what it looks like when you run it. So there's the result. I made a plot, which is not shown in the script here, but I made a plot showing Euler's method, ODE 45, and the exact solution. And you can see clearly that ODE 45 is doing really, really well at approximating the exact solution. So there you have it. Now you know how to solve systems of ODEs and second-order ODEs in Matlab using Euler's method and ODE 45. So now it's up to you to practice some of those methods. And some of that will be done in lab, and then some of it you can do on your own. I've posted some code samples on D2L.